Welcome to Maths with EJD. In this video, I'll be talking about game trees and decision nodes. In the previous video, I talked about extensive game forms where players, where players play their game sequentially. Player A does something, and based on what player A does, player B does his own thing, and the whole thing continues like that. So game trees and decision nodes are a very good way of representing extensive game forms. So let's go for that. First of all, let's look at the definition of a game tree. So a game tree is a visual representation of an extensive. So game tree is a way by which you represent extensive game forms. So a game tree is a visual representation of an extensive form game illustrating the sequence of decisions, actions, and outcomes. Okay, so let's go ahead and look at the components of this. Components of game trees. Components. Okay, first of all, we have nodes. This actually represents decision points or outcomes. Okay. Nodes represent decision points or outcomes, as we're going to see very soon. And we also have branches. We have branches. Of course, we are talking about a tree, right? So trees have branches. So, um, so the branches actually represent actions available to the players. Then we have labels. Okay. So this actually indicates which player makes the decision and the available actions. All right. Now, I also like to add that okay, maybe this is just by the way, right? Okay, okay, I guess I can talk about that later. Let's take an example to drive this point home. When I introduced the idea of extensive game forms, I actually gave a particular scenario of sharing $100 in a particular way. So let's go and consider that scenario again. So say the scenario we have. Wonder why I keep writing scenario. So we have this scenario, right? That the two players, A and B, decide how to split $100. Okay, that's the situation. Two players want to split $100. So of course that situation is a kind we can consider it as a kind of game where player A chooses player A actually has a choice between splitting fairly. Of course, a fair splitting will be $50. Each person gets $50, right? Or player A can actually choose to do it unfairly. That is where the real game is. So if player A chooses to be unfair, such that player A gets so we have $90 for player A and $10 for player B. So that's where the actual game is. So the next thing is if A chooses unfairly, Of course, if it chooses to be fair, then it ends there. Each person gets $50 each. But if it chooses unfairly, in fact, I guess I want to really emphasize these options. So first of all, I'm talking about fairly. So let me capitalize that. So fairly is $50 each. Then it can be unfairly where A gets $90 and B gets $10. So if A chooses unfairly, okay, B can B now has two choices. B can accept. So I'm also going to capitalize that. So the options available to B will be accept. B can accept or reject the split. Okay. So if B rejects, right? If rejected, both get nothing. Both get $0. Okay. So the whole idea of a game tree is to represent this sequence of events in a game using a game tree. All right. So let's go ahead and look and do the game tree representation of this scenario that has been painted. So game tree representation or game tree representation, right? So see what happens here. Imagine this is player A here, or should I just say player A? Let me actually say player A like this. Okay. You have player A right here. So player A has two options. Player A can choose to be fair or unfair. Okay. If player A, just like what we have already, right? If player A chooses, uh, so if player A is fair, right? That's automatically 50-50 for both player A and player B, right? Now, the next thing now, we have player B. So just like we have already, if A chooses to go unfair, so it means we have player B around here. We have player B here. So if A chooses between splitting fair, okay, if A chooses unfairly, so imagine, uh, okay, we have fairly and unfairly, right? This is fairly, and this is unfairly, okay? Or I mean, I can even leave it like that, right? So fair or unfair. So if player A goes unfair, so player B has two choices. All right. So of course, this is a node now. This will be a node. This is also another node now, showing each player and the labels too. So if player A chooses to go unfair, right? Player B can accept or reject. So player B has two options, either to accept or reject. Okay. So if player B accepts, that means player B is settling for 90-10, meaning that player A gets $90 and player B gets $10. But if player B rejects, everybody gets nothing. Okay. So this is a very good example of a game tree. All right. This is a very good example of a game tree. But interestingly, right, for this same game, right? So the focus is on game tree, but I just want to also point it out that it's possible to also do a kind of matrix representation of this game tree. You know what we've been doing so far is that matrix representation thing. So we represent the payoff matrix. We have a payoff matrix. Okay, so let me now say uh matrix representation. All right. So we have game tree representation and now matrix representation. So in this case, we have uh we have player A. Imagine we have player A here, and we have, or better still, it's better to draw. Let me draw this first. Mm, okay, something like this. So we have player A who can either be fair or unfair. And we have player B who can either accept or reject. Accept or reject. So we have the payoffs. Now, if player A is fair, right? If player A is fair, no matter what player B does, they both get 50-50. So fair accept or fair reject, it's all 50-50. Okay. It doesn't matter what B does in that case because A has chosen to be fair. But if A is unfair, just like what we have here, so from this game tree, if player A is unfair, then player B has two options to either accept or reject. So if player B accepts, that will be 90-10, 90 for player A, 10 for player B. But if player B rejects, they both get nothing, 0-0. So we can represent that game tree even as a matrix like that we've been used to already. So that's how that goes. Okay, that's how that goes. And I guess that will be the end of this particular one. Um, okay, well, except that I can sign out with this conclusion, or better still, call it an interpretation if you like. Conclusion or interpretation. Let me just go for interpretation. So each path from the root, each path from the root to a terminal node, each path from the root to a terminal node represents a possible represents a possible outcome based on players' decision, based on players' decisions. Okay. So if we come back here, right? Uh, this is actually this is what we can call this is like the root node. This is the root node where it all starts, and then this is the well, we can call each of this the terminal node, where a final decision is reached based on their activities. Terminal node, like that. So um okay, so that's how that goes. All right, so that's the end of this particular one, talking about and game tree and decision nodes, as you have seen already, and the fact that we can represent game trees as we can have a game tree representation as well as a matrix representation, and that's how that has been. So in the next video, I'll be talking about SPNE. SPNE is subgame perfect Nash equilibrium. So watch out for that. Because of that, you want to sign up to this channel and hit the notification bell so you can always get alerted every time a new video is released. You also want to comment to let me know if you want me to teach a topic or solve a problem. I might just be able to find time to do that. Then like and share so that more people can have access to this great content. Till I come your way again, keep playing the game of life with sense. Thank you.